Today, we want to look at vector fields and parameterized curves. We want to take these two great tastes that taste great together and put them together. So when we talk about parameterized curves, we're talking about a one-dimensional curve running through three-dimensional space. I'm going to put everything in a plane so I could draw it, because I tried to draw it in the space and it just, the pen is not like working. So I can't draw three-dimensional curves. So let's suppose that we have some curve running through space. So I drew this curve in space. Presumably there's some kind of parameterization. Oh yeah, we should have an orientation on this curve. One of the things that we saw about parameterized curves is that when we parameterize a curve, we assign some kind of direction on it. So there's some direction. We're going from generally from left to right, but although at this point, the curve kind of turns back, but then goes this way. So presumably this curve is parameterized and has this orientation. It's going from P to Q. It's a one-dimensional curve in n-dimensional space. Doesn't matter how big the space is. At each point on this curve, the vector field, it has a vector. At every point along this curve, there's a vector from the vector field. So the curve is in space. It's a path through a vector field. So we're imagining this curve as a path through a vector field. That means at every point on this curve, there is a vector that comes from the vector field. So maybe at this point, the vector field is, at this point, the vector says this is the vector field. So if this is point A, here's a vector field at point A. Maybe at some other point, at some other point B, there's the vector field evaluated at point B. That's what a vector field does. At every point, we assign a vector. So at every point on this curve, there is some vector. Right. This is the template. Correct. Here's a point C, here's another point. And then we have a vector field. The vector field, throwing a vector at that point. At every point on the curve, there is a vector from the vector field. I've only drawn 4 of the vectors from the vector field. At every point on the curve, we can imagine a tangent to the curve. That represents the direction that we're going on that curve at that point. At every point on the curve, we have some tangent. on the curve, we can build a tangent vector. The tangent vector just says we're going that way. So if I have a path that I'm walking back and forth right now, I have a tangent vector like that. Then I stop here to keep you from copying things down. My tangent vector is 0 because I'm not moving. And then I pace back that way. Here's my tangent vector. Here's my tangent vector. And then I turn around. There's my tangent vector. Now, if I want to make the class more three-dimensional, I can have my tangent vector go this way. And then my tangent vector drops to 0 because I'm looking at the clock. And then, okay, half an hour more, and then tomorrow one more day. That's running in the background. I'm not supposed to say that out loud. And then I set my tangent vectors. I go, here's my tangent vector, so I'll start going this way. And then I make more tangent vectors. It'll take too long, and then I slow down at my tangent vector. So at every point on the curve, there's a tangent vector. In particular, at these 4 points, there's some tangent vector. If we parameterize the curve, let's give the parameterization a name. We'll call it R of t. R for position. Very well. So R of t is our parameterization of the curve. There's an R right in parameterization, so it makes perfect sense. The tangent is just the derivative of each of the components of our parameterization. So the tangent is R prime of t. So at that point A, we have a tangent at that of tangent to the curve at that point. That would be R prime at A. At every point, we have a tangent to the curve. We have 2 vectors at every point, one from the vector field and a tangent to the curve. So at every point, we've got 2 vectors. At every point on the curve, we have 2 vectors. Tangent to the curve and a vector from the vector field. The angle between them could be anything. The way we define the angle between them, we'll probably use the shorter angle, because there's always 2 angles, right? But we'll use the one between 0 and 180. So instead of saying 210 degrees, we'll just call that 150. So at every point, we see 2 vectors. At every point, we have 2 vectors. What might we do with these 2 vectors? Multiply. What ways do we have to multiply? Dot product or cross product. We got 2 ways to multiply. Cross product, dot product. It makes sense that I would immediately think about multiplying these 2 vectors at every point along the curve. Because that's what integration is about. Integration is multiplication, but one of the factors is continuously variable. I want to find the dot product of the vector field and our direction along the curve, and just figure out what that could tell us. We need some kind of default thinking. The default thinking could be if we think in terms of the effect of the vector field on the path. So think of the vector field as the wind, and think of the path as us walking in the wind. Sometimes the wind is pushing against us, but not directly against us. It's kind of coming off to the side, but there is some component of this vector field vector that's pushing against us, slowing us down, or just making us work harder to maintain this vector. Sometimes the wind is directly behind us and pushing us along, so we have to do less work to maintain this path. Sometimes the wind is going across direct perpendicular to us, so it's not pushing us along our path at all. Sometimes the wind is pushing directly into our face, making us work harder. So sometimes the angle between the vector field and the path is 0 degrees. Multiply by 1. Sometimes the angle between the vector field and the path is 180 degrees. Multiply by -1. Sometimes the vector field is perpendicular to the path. Multiply by 0. And sometimes it's just some angle. Multiply by the cosine of the angle between the vectors. That's what we want to think of when we think of a path flowing through a vector field. Any questions? How's everybody okay? Now, this is not in great detail, and this is only one of the ways that we're going to come up with vectors. This is just the path version. But what we're going to want to do is, let's say this path is, the curve is C from P to Q. We're going to want to take the vector field and the direction of the path. We'll find a dot product. And then we will add up all these values along the curve C. This is called a line integral. The line is this curve. We say line integral, we're talking about all the points along the curve. The language, the notation that we're using here is the same notation that we always use. I want to calculate this f dot dr for one of our factors. In this case, both of our factors are continuously variable. But we're going to evaluate f dot dr at all the points on the curve C, because that's what the integral tells us to do. Is evaluate f dot dr at all those points, then add the results. We know that when we're adding results, we have to do some kind of antiderivative wizardry. That's how we find a continuous sum. But it's the same thing that we always do. Any questions? Comments? The +1 dimension of this is instead of instead of a curve in R3, imagine a surface in R3. At every point on that surface, the vector field is doing a thing. And we're going to look at how the vector field flows through the surface. And so we're going to want to know the angle between the vector field and a vector normal to the surface. At every point on the surface, we're going to grab a normal vector. And then at every point on the surface, we're going to look at the vector field flowing through the surface. We're going to find a dot product at all the points on the surface and add up those dot products. Any questions? Comments? Snide remark? How's everybody okay? Everybody looks very thoughtful. That's what you're supposed to look like. You're supposed to look thoughtful. So. That's how you deflect questions. If you have a professor, you have a professor that likes to like randomly ask you questions, and be like, "Oh, you answer this question," like, "Oh, ah." The defense against that is to look like you're still thinking about it. So it's like, so you can't just sit there. If you look like this, that's like, that's the sickly gazelle, right? Lion's gonna come, just drop right down from the ceiling and roar, right? They're gonna call on you for that. So you want to look like you're still thinking about it. It's like, oh, hang on, I'm still working this one out. So look thoughtful. You can look extra thoughtful by like holding your face up. Like, oh, this is so heavy, I gotta hold my face up. Put your hand on the chin. Then if you just put on a smile, it's like, oh, GQ pose. All right, I can't do GQ pose. I'm not a model. But that's it. It's like, just look thoughtful. Don't overdo it though. It'll be like, oh, right? Because then you're like, oh, then they'll think something wrong with you. You don't want your professor to think there's something wrong with you. Also, some professors haven't gotten used to the idea that you might be angry at them because you like assign them work. They're assigning you work. And you have to do the work. And then they took off points just because your answer was wrong. And so you're all angry. So you don't want to look mad. You'll be all, right? You gotta modulate that shit, right? Gotta get that still thinking. Don't call on me yet. I'm still thinking. Oh, you called on someone else. Oh. Then don't bail. Like pretend to pay attention to what the other students say while they stumble through it. You know what I mean? This is important stuff. This is like, they don't teach you this stuff, is what I'm saying. I don't know. It's just like doing school. The reason is your GPA isn't a measure of like how smart or educated you are. Your GPA is a measure of how good you are at school, right? That's what it is. It's how good you are at school. Like when you take standardized tests, what do standardized tests measure? No, it measures how good you are at taking standardized tests. That's what it means. If you're really good at taking standardized tests, you'll score well. If you're not very good at taking standardized, that's the only thing we're finding out here. And someone's like, oh, I got a 1600 on my SATs. I'm like, well, that's great. You're really good at standardized tests. That's it. That's the end of it. So those of you are like, oh, no, but I got like a 1580 on my SATs. Well, you should still be proud of that. I mean, that's still hard to do. But if you got like 1,000 on your SAT, don't feel bad about that. Maybe you're just not good at standardized tests. You know what I mean? Is anybody who has taken an SAT? Long time ago? I have.
I take the practice.
Here's some insider information. So for a while, when I started off my teaching career, I was teaching high school. Yeah, it was exactly the disaster you're thinking it would be. So because that doesn't pay very well, on the side, I taught SAT prep classes. So parents would hire the company that I worked for me to train their kids to get a better score on the SAT. And I only did the math portion. How much math content did I teach those students?
I think that was like 500 points.
Yeah, it's like 800 up to 800 points. But I taught zero math content. I did not teach people how to do math, to do the math part of the SAT. I taught them what the test looked like and how to defeat the test. I specifically trained them to fight the test, not the math. Because if you're in a standardized test, if you're in the math SAT or the math GRE, because it's the same stuff, if you're taking that test and you start to do the math that you learned in class, you're taking way too long on that problem. You teach people what the test looks like so that when they get there, they don't have to figure stuff out. You just react. You know what I mean? So on average, the company got students to score 50 points higher, not by teaching them any math, just by teaching them how the test works. Think about how good your driving test would be if they just told you exactly the path that you were going to take. You could just get ready for it. You could figure out what the problems are. See, they're going to take you through this intersection specifically to make sure that you can safely make a right turn on a red light. Or because it's a trick question and you can't make a right turn on a red light at that particular intersection, and they're watching for that because they want to automatic fail you. You know what I mean? They're going to see if you can merge. where are they gonna see if you can merge? If they gave you the path, they gave you the path of the driving test, where are they gonna ask you to merge? They're gonna wanna see these things, certain things. You know what I mean? Anyway. That's all beside the points. Let's take a look at some problems. This is kind of a classic problem from your calculus past. I have a hemispherical pool with a radius of 4 meters. I don't know why I made this thing so big, but there it is. And it contains water to a depth of 2 meters. I realize the picture doesn't match up. Water is up to half the depth, but the pool is not half full by volume. The pool is only half full by depth. I have two very simple questions. Write the triple integral for the volume of water in the pool, and then find the volume of water in the pool.